today is the last lecture, and I would like to have a group photograph, but I think we'll do it during the break because some students come late. Okay, so the goal today is to explain the E2 term in Loray's spectral sequence. Okay? So the Loray spectral sequence for a fiber bundle says that there is a spectral sequence that converges to the cohomology of the total space, and the E2 term is HP of a good cover U with coefficients in HQ. And that HQ is the cohomology of the no, just a minute. Yeah, right. It's with coefficients in HQ, and that's equal to the cohomology of the base tensor with the cohomology of the fiber. Okay, yeah, for a fiber bundle. With fiber F. Okay? And this is very useful in the calculation of the cohomology groups of either E or M or F, given that we know the cohomology groups of two of them. Okay. Okay. So to explain this, well, you see here, this pre-sheaf HQ turns out to be locally constant on a good cover. And so under certain conditions, it's a constant sheaf. And then you can use the check de Rham isomorphism to relate it to de Rham cohomology, okay? So first we want to determine a condition under which a locally constant pre-sheaf on a good cover is constant. And okay, so let me explain the setup. So you have X is a topological space, and then U, eventually it will be a good cover, but here it's just an open cover. Okay. Yeah, so like if you have a circle, then we have an open cover. Okay, this one happens to be a good cover. And then you have a simplicial complex called the nerve that's associated to the open cover. So the nerve associates a vertex to each open set. And then an edge if the intersection is non-empty. Okay, so this is the nerve of the open cover. And then you can take the barycentric subdivision, and that means you take the midpoint of each edge, and if there's a two simplex, you take its barycenter, and So the barycenters represent the finite non-empty intersections. This one is U02, this is U12, this is U01, okay? So that's the barycentric subdivision. Of the nerve. The nerve is a simplicial complex, and the barycentric subdivision is a simplicial complex. And if you have a pre-sheaf on the open cover, so that is, well, it associates to each non-empty finite intersection a group, right? So it is, yeah, so it's actually a functor, right? It's a contravariant functor from the category of all non-empty finite intersections of the open cover with inclusion maps, right? Given to any two adjacent vertices, you know, like one open set is a subset of the other. So those are the morphisms and inclusions. And that category, well, it's really the barycentric subdivision of the nerve. Okay? And the inclusion can be indicated by an arrow, right? So this is included in this. This is included in this. Okay, so actually you have, this forms a category, and then a pre-sheaf on an open cover is a contravariant functor from this category to the category of groups. Okay, and we are only looking at abelian groups. Okay, so you can, yeah. So you can view a pre-sheaf, you know, as a group on each vertex of the barycentric subdivision F. Yeah, so this would be F of U0, F of U1, F of U2, F of U12, and so on. And it's a contravariant functor because the inclusion goes this way, but the restriction would go the other way, you know. This would be rho from U2 to U12, okay? Yeah. Okay. Now, a pre-sheaf is locally constant. On the open cover U, if and it's with a fixed group, with group G, okay? If all the, you know, okay, if all the groups are G and the restrictions are isomorphisms, yeah, so rho, say, okay, V alpha to V beta are isomorphisms. And it is constant with group G on U if, okay, all the groups are G and the restrictions are identity. Okay? Okay, and so last time, you know, I gave you an example where you have a locally constant presheaf, say all the groups are Z, but the restrictions are not all identity. So like, it could be that you have identity everywhere, but at one point, no, on one of the edges, the restriction is -1. So this is locally constant, but not constant. Okay? Okay, so the theorem we're going to prove is that every locally constant presheaf is constant if the edge group is trivial. So the edge group is the combinatorial analog of the fundamental group. Okay? Yeah. What's the edge group of this simplicial complex? We did that last time, right? Yeah. So the edge group consists of all the loops that are not equivalent to the identity. So do you remember the edge group of this? I mean, it's just, it's Z, okay? It turns out to be the same as the fundamental group. In fact, there's a theorem that says that the edge group of a simplicial complex is the same as the fundamental group of the underlying topological space. Okay? Yeah. So this is basically the circle, right? And the fundamental group is Z, the edge group is Z. Okay? Yeah. So because the edge group is not trivial, you see, you can have a locally constant presheaf that's not constant. But this theorem is that if the edge group of the barycentric subdivision of the nerve, okay, with some base point is trivial, then, well, and it has to be path connected because, yeah, if you have a base point you're only looking at loops starting at that base point, so you cannot see, any other components, right? So, yeah, so, yeah, when we talk about the edge group, it means this is path connected, okay? So if the edge group is trivial, then every locally constant pre-sheaf on U is isomorphic to a constant pre-sheaf. Okay. Okay, so that's what we want to prove today. And so we're going to start by defining a map from the edge group to the group of automorphisms. Okay, so, and this is called monodromy. Yeah, so like if a pre-sheaf is locally constant, then all the restrictions are isomorphisms. So you can take its inverse, and therefore, the restriction can actually go both ways. Okay? In any direction. Okay, I want to prove a lemma first. Lemma. Okay. So suppose you have two simplex. Say V0, V1, V2. Okay, now, if you have a two simplex, now on any edge, one of the open sets has to be a subset of the other, right? Because, yeah, okay. Yeah, so like, right, so, because this point would represent the intersection, and if you take the barycentric subdivision, and this point is V 0, 1, 2. So in the barycentric subdivision, if you have a two simplex, I mean, any edge is a containment relation. But if you are just given three vertices, okay, you may not know like which one is contained in which other. So, so if you just know that there are three vertices, okay. Oh, yeah. Let me not use. Okay, so I'm going to call this W because the V is different. Okay. Yeah. Oh no. Yeah. So if I have three vertices, okay. So any three vertices, I don't know which one is contained in which other one. Okay, so span a two simplex in NU prime. But, okay, so just a minute. Well, I mean, if I know, say, which one is contained in which other one, say, if I know V0 is contained in V1 is contained in V2, then I know the restriction from V2 to V1, followed by the restriction from V1 to V0 is the restriction from V2 to V0, right? I know that. That's part of the properties of a restriction map. If you have a containment. But if I don't know which is contained in which, then I may not have this, right? Because this is assuming that V0 is in V1, is in V2. But the lemma is that it doesn't matter how they are contained in each other. This is always true, okay? So I'm going to write rho ij for the restriction from Vi to Vj, okay, just to make it simpler. So, yeah, even though you don't know how they are contained in each other, you can still say that rho 2, 1, rho 1, 0 is rho 2, 0. Okay? That's the lemma. Okay? And this is useful because then you can always write this down without knowing, you know, the containment relations. Okay. Okay. So let's try to prove this. Yeah. Okay. So proof. Yeah. I have a two simplex. In the barycentric subdivision of the nerve. Okay. Now each edge represents a containment relation. So so for example, like V0, V1, this edge, it means either V0 is contained in V1 or V1 is contained in V2, okay? So in the barycentric subdivision, you always have this. And yeah, so like when you have three open sets, there's one that is the smallest and one that is the largest. So you can permute them in such a way that you have that containment relation. So there exists a permutation of 0, 1, 2 such that the smallest one you call V sigma 0, and then the largest one is V sigma 2, and the middle ones is V sigma 1. Okay? You can permute the three open sets so that you have this containment relation. And then without loss of generality, you can relabel them. You may assume that you have V0 contained in V1 contained in V2. Okay. And then in this case, you know that rho 2, 1 followed by rho 1, 0 is rho 2, 0. Okay. But because F is locally constant, and I should put that in the hypothesis, right? So assume F locally constant. You need that so that you can take the inverse of any restriction map. Okay, yeah. And so the inverse of rho 2, 0 is rho 0, 2, right? and so you can, rho 0, 2, rho 1, 0, rho 2, 0 equals rho 0, 2, rho 2, 0. You multiply both sides by rho 0, 2, and then rho 2, 0, rho 0, 2 is rho 2, 2. When you restrict from an open set to itself, that's the identity. Okay, so you have this relation. And what I want to show is that I can permute these three numbers and it's always true. So like, let me see. What I want to prove now is I want to prove rho 1, 0, rho 0, 2, and rho 2, 1 is also the identity, okay? Now, how can I prove that? Okay, so rho 2, 1, okay, rho 1, 0, rho 0, 2, that's here. Yeah. So like from the first line, what you get is that rho 2, 1 is the inverse of rho 1, 0, rho 0, 2. Right? That's from group theory. In group theory, like if an inverse is the right inverse, then it's also the left inverse, okay? So this will be, these two are inverses to each other. Yeah, so you'll get the identity, right? Rho 2, 1 is rho 1, 0, rho 0, 2 inverse, and then rho 0, 2, rho 1, 2, right? So, yeah. Okay. Okay, so, yeah, so I can start with 2, or I can start with 1, and similarly, I can start with 0, rho 0, 2, rho 2, 1, rho 1, 0 is also the identity, okay? So no matter how you permute the three numbers, you always get the identity. And well, this is equivalent to, what is this equivalent? This is equivalent to This is the, no, let me see. Oh, it's equivalent to the inverse of this. So rho 0, 2 times rho 1, 0, rho 2, 1. Right, this is equivalent to this. Because you just multiply both sides by the inverse of rho 2, 0, okay? Okay, so, yeah, so it doesn't matter what the containment relations are. You always have the same relation as if, you know, these are contained in one another, okay? Yeah, okay, so that's useful. Okay, so what does that say? What that says is that when you have this two simplex, you know, if you go around it, you always get the identity. Okay? It doesn't matter where you start. Okay, yeah. Yeah. So the corollary is this, that going around a two simplex in the barycentric subdivision of the nerve always gives the identity. Okay, and okay, now in a simplicial complex, let me see. So let's say some of these are filled in. So in the simplicial complex, whenever you have an edge, then you have a restriction map, right? But and the restriction maps are isomorphisms. Okay. Oh, and so if you have a pre-sheaf, okay, then there's a group here, and there's a group here, and a group here. Okay, yeah. So every path, you know, will give you an isomorphism from this group to this group. Every path from V0 to V1 gives you an isomorphism. But, you know, there may be many ways to go from one vertex to another. So that's one way, but that's another way. So that also gives you an isomorphism. Okay? And usually there are different isomorphisms. But I'm going to prove a theorem that says that if the two paths are equivalent, then you get the same isomorphism. Okay. So this path, this white path, okay, may not give you the same isomorphism as the pink path, but let me do like this do it this way, okay? So I have this green path. The green path is equivalent to the white path because you have a two simplex here. So this path is equivalent to this path, right? That's part of the definition of equivalence. Whenever you have a two simplex, then going around on two sides is the same as going along the third side, okay? Yeah, so the theorem is that equivalent path gives the same isomorphism, okay? Yeah, let's prove it here. Theorem. I want to make sure that I state all the hypotheses. So we are always talking about locally constant presheaves. That F be a locally constant presheaf on an open cover of X. So equivalent edge path in the simplicial complex, the barycentric subdivision of the nerve, at a vertex V naught induce the same isomorphism. Oh, so equivalent path, no, not at V naught, but equivalent path from V0 to V1, equivalent path from V0 to V1 in the barycentric subdivision induce the same isomorphism from F of V0 to F of V1. Okay? Okay. So, I mean, we just have to, so each edge induces an isomorphism. Okay, so we just have to check that the three type of equivalences give us the same isomorphism. Okay? Yeah, because the equivalence relation is generated by three basic equivalences, right? So we only need to check the three basic equivalences. And the first one is that if you have a path and a vertex repeat, then what is that equivalent to? Like, how do you simplify this? If you have a path in which the vertex repeats, Yeah, it's just V, right? It's just one V. Okay. So that's the first type of equivalence. And what's the automorphism that it induces? So it induces from V to V, that's rho V V. Well, rho V V is just the identity. So yeah, okay. So like if I have two things before, so like if I have U and W here, okay, then I would have rho this would be UV, and then VV, and then rho VW, right? And then here you have U here and W here. So this one would induce rho UV rho VW. And you see they're the same because rho VV is the identity. Okay? So this sequence of isomorphisms is the same as this sequence. Okay? So when two paths are equivalent under the first type of basic equivalence, they induce the same isomorphism. Okay? And now let's do the second type of equivalence. Okay, and can somebody tell me what the second type is? Okay, you go from U to V, and you back to U, okay? And that's equivalent to, well, going from U to V and back to U, that means you cancel them out. So it's just, what is that equivalent to? That's just U, right? Okay. And this type of equivalence relation, okay, it induces rho UV, rho VU, rho, oh yeah, rho UV, rho VU, and oh, and then like if I again put say a W here, and then a Z here, so I will have rho WU and rho UZ, and then here it would be rho WU, rho UZ, okay? But these two are inverses, so that's the identity. So again, this type of equivalence relation induces the same isomorphism. Okay. Okay, and then the third type, oh, oh, right, you are right, yeah, because it's a contravariant functor, right? Thank you. So here, if you're going that way, it has to go the other way, right? So let me see. So you actually have to do this first. Yeah, right. So this should be WV, then VV, then VU. Thank you. Yeah. And then this should be WV and then VU. Okay, yeah. All right. And here I should start with Z. So ZU and then UV and then VU and then UW. Okay. And this should be ZU and then UW. Okay. Yeah. All right. Now let's look at the third type of equivalence relation. So the third type is when you have a two simplex okay, this is filled in. And then, okay, then the equivalence relation is that UVW is the same as UW. Okay, so UVW is equivalent to UW. And they induce rho WV, rho VU, and rho WU. Okay? So this is where you need the lemma. Okay? You don't have to know the containment relation among these three open sets. Okay. You know that this is always equal to that. So by the lemma, these are equal. Okay, so because the three basic equivalence relations induce the same isomorphisms, then any two equivalent paths will induce the same isomorphism. Okay? And yeah. Okay. Okay, and so so what that says is that so equivalent loops. Yeah. Equivalent loops at V naught in the barycentric subdivision will induce the same automorphism. Okay? So a loop is a path that begins and ends at the same point. So induce the same automorphism of f of V naught. And so this gives you a map V from the edge group to the automorphisms of F of V naught. And this map is called the monodromy. Of the locally constant pre-sheaf on the open cover U. Okay. All right. So let's take a break for 10 minutes and then, we'll prove the theorem that states the condition under which a locally constant pre-sheaf is constant, and then we'll apply it to the Ray spectral sequence, okay? But I would like to take a group photo of everyone. Now, what's the best way to do that? Like if I take a photo like this, I wonder if you will all show up. So, yeah, I think the problem with this is that some people in the back will be very small and uh, and then maybe it's hard to see, but I'll take one this way, and then maybe you can all come up to the stage. We'll take another one that way. Okay, so, all right, so, okay, put on your best face. Put on your best smile. All right, so please look at the camera. 1, 2, 3. Okay, another one. 1, 2, 3. Okay, and now, can you all come up to the stage? And then I will ask a secretary to take a picture so that I can be in the picture too. So somehow line up on the stage. Yeah. 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 Okay. I want to make a correction here. So if you have an edge path from V0 to V1, because a pre-sheaf is a contravariant functor, okay? So it reverses the direction. So the isomorphism should go from f of V1 to f of V0. If your path goes from V0 to V1, then the isomorphism should go backwards from f of V1 to f of V0. Okay? Yeah. Okay. So, okay. We now want to state a condition under which a locally constant pre-sheaf is constant. And this is the theorem. So let U be an open cover of a topological space X, okay? And if the barycentric division of the nerve is path connected, and the edge group is trivial, then every locally constant pre-sheaf F on U is isomorphic to a constant pre-sheaf. Well, we should specify the group. So every locally constant pre-sheaf with group G, okay, is isomorphic to the constant pre-sheaf with group G. Yeah. Okay, so what we're going to do is to define an isomorphism between these two pre-sheaves. The constant pre-sheaf is denoted G bar. The constant pre-sheaf with group G is G bar. So an isomorphism between two pre-sheaves is an isomorphism of the groups of the pre-sheaves that commute with the restriction, right? So, yeah, so for every open set V in the, no, yeah, right, an element of the barycentric division, subdivision of the nerve, it's really a finite intersection of open sets, right? So, that's V is an open set. So every V in this simplicial complex we want to define we want to define an isomorphism. Let me see that I call phi of v from f of v to g bar of v. So I want to define this map. They are both G. So as follows. Okay, now we have a base point, V naught. So we first, fix an isomorphism. V naught. So we fix an isomorphism. And now, because f of v, because any two paths, any two equivalent paths induce the same isomorphism. Let me see. So, oh yeah. So because we're assuming that the edge group is 1, that means any two paths are equivalent. Maybe I should prove that first. Okay. So lemma if the edge group is 1, then any two paths from V0 to some V1 are equivalent. Okay. And okay, so let's say you call the two path alpha and beta. Then alpha, okay, times beta inverse is a loop. Okay? At V naught. But every loop is equivalent to the identity. So alpha times beta inverse is equivalent to the identity. And well, I mean, you have a group, right? So yeah, so the equivalence class is equal to the identity. And so alpha is equal to the equivalence class of alpha is equal to the equivalence class of beta. Okay. The identity is just the equivalence class of the constant path of V naught, right? But yeah, okay. So under the assumption that the H group is the identity, then any two edge paths are equivalent. Okay? That's because any loop is equivalent to the identity. Okay? And so so that means like any two paths will induce the same isomorphism. Yeah. So like I fix an open set as the base point. Uh-huh. Uh-huh. So fix an isomorphism phi of u naught from f of u naught to g bar of u naught. Okay. And then because yeah, so because we're assuming that the barycentric subdivision is connected, so we have a path from u naught to v. Okay, we have a path from v to u naught, and so that is going to give us a restriction row of, let me see, so this would be, okay, yeah. If the path goes from v to u naught, then this would go from u naught to v, right? Yeah. And we can write this because it's independent of path. Okay? So, so for any two elements, let's say uv in here, so rho of uv from f of u to f of v is defined independent of path. Okay? Because under our hypothesis, any two paths are equivalent, and equivalent paths induce the same isomorphism. Okay, so you have an isomorphism here, and so this one is phi u0, and so, but so you have a map going this way. This one I define to be phi v. So phi v is defined to be phi u0 composed with rho u0v inverse. Right? You can go inverse and then this, and that's phi v, okay? And yeah, so that's my phi v. For every open set, I define an isomorphism from f of v to now g of u naught, and then okay, and then g, I have g of v here, okay, but this is g bar of v, okay? But because g bar is the constant pre-sheaf, its restriction is the identity. And no, just a minute. That's not phi of v. Okay, that's just some map. No, I define phi of v to be this map. So I have this map, and then I follow by the identity, and then this map. That's my phi of v. Okay. And so you see, yeah, so this is good because this says for these two open sets, now you have these isomorphisms, and it commutes with the restriction. Okay? So it's a homomorphism of pre-sheaves. Okay? But what we need to check is that for any two open sets, okay, the homomorphism commutes with the restriction. So yeah. So suppose U is any other open set. In NU prime, okay? So then you have f of u, and you have defined phi of u to g bar of u. You have defined that already, and it fits into a commutative diagram, V naught. Gosh, this is V naught. The base point is V naught. Right, by definition, we have this commutative diagram for U, and then we also have a commutative diagram for V. And so this is V, okay? Okay, and then the thing is, okay, so given these two open sets, we want to show that the restriction, right, commutes with the restriction of the constant pre-sheaf. And where's my red pen? Oh, here. Yeah, but these are all isomorphisms. Because you have a locally constant pre-sheaf. So all the restrictions are isomorphisms. So so you have a map here this way, and it's rho UV. And so rho UV, it's rho V naught U inverse. Take the inverse of this, followed by rho V naught V. This is rho U V naught, rho V naught U. Okay? So you know that you have this relation because we proved a lemma earlier that for any three open sets, you know, it doesn't matter whether you know how they are containing each other, you always have this relation. Okay? Yeah, so that go there. And this map here is just the identity. Okay? So what I have done is that I have defined a pre-sheaf homomorphism, right, that commutes with restriction maps. And these are isomorphisms. So that proves that F is isomorphic to G bar. Okay? Because for any 2 UV, you have this commutative diagram. Okay? So this diagram proves that F is isomorphic to G bar. Okay? And we are assuming that F is locally constant so that all the restriction maps are isomorphisms. Okay. So now let's apply this to spectral sequences. Oh, now there is a theorem, okay, that says that for, let me see, yeah. So for X path connected, the fundamental group of X is isomorphic to the edge group of the open cover, the nerve of the open cover. And that's isomorphic to the edge group of the barycentric subdivision of the open cover. Yeah. And this is, so you can find the proof of this in the book. And then there's a theorem that says that the edge group of a simplicial complex is the same as the fundamental group of the underlying topological space. And because these two have the same underlying topological space, you know, so they have the same edge groups. And that's in a book by Armstrong on topology. Okay? Yeah. And so if you have a topological space, usually your assumption is on the fundamental group. Okay? So if the fundamental group is trivial, then the conclusion holds of the theorem that we just proved. Okay, okay. So now let's apply this to the spectral sequence of a fiber bundle. So Okay, now because of time constraint, I'm just gonna state a theorem, a proposition without proving it. Okay, so we are looking at the fiber bundle with fiber F. And HQ is the presheaf on X whose group is HQ of pi inverse of U. So that's a presheaf on X. No, presheaf on the base, M, on M. Okay. And so the first thing you prove, and that's not too hard, is that this presheaf is locally constant on a good cover of M. And now let's assume that M is simply connected. Assume M simply connected. Well, then the edge group, the fundamental group is trivial, so the edge group of the barycentric division of the nerve is trivial. And so HQ is constant. Constant presheaf. With group HQ of U. Now, so U is in the open cover. So it's contractible, right? Because you have a good cover. Well, it's in the C infinity category, it is diffeomorphic to Rn. And so it's contractible. And so this is HQ of pi inverse of U. Okay. Because U is contractible, the vector bundle over it is trivial. So it's U cross F. And if U is contractible, it doesn't, by the Kunis formula, it doesn't contribute any cohomology. So this is just HQ of F. Okay. So this is the group. So HQ is isomorphic to the constant presheaf with group, the Qth cohomology of F. Okay, and now we need a further assumption that the Qth cohomology of F is finite dimensional, so it's just finitely many copies of R. And so this is just the direct sum. Oh, well, let me see. So, yeah. So this is assuming HQ of F finite dimensional. Okay. Yeah. And let's write down the E2 term. So E2 PQ in the Ray spectral sequence is the check cohomology of the good cover with coefficients in HQ. And that's the check cohomology of the good cover. And then HQ is just the constant pre-sheaf. And well, I guess if it's just R, then you have the check the RAM isomorphism. If you have finitely many copies of R, you can decompose it so that you have finitely many copies of the check cohomology with coefficients in R, okay? And now each of them, because you have a good cover, each of them is isomorphic to the RAM cohomology. Just a minute, this is HP. Okay. So that's the check the RAM isomorphism. Okay, so you have as many copies of HP as the dimension of the cohomology. And so this is isomorphic to HP tensor with, so let's say we have M copies. Okay, say this is R to the M. So you have M copies. Yeah. Well, you can write it this way. M copies, right? Because when you tensor with R, you just get the vector space itself. And so that's HP of M tensor with HQ of F. Okay. Okay, so that's why in the Ray spectral sequence, you can identify E2 with the tensor product of the cohomology of the base and the cohomology of the fiber under two hypotheses. One of them is that M is simply connected, and the other is that the cohomology of the fiber is finite dimensional. Okay. Okay. So that's the end of the course. And I'm glad that I've gone this far. So I want to thank you for all your feedback and your questions. I'm going to write a new edition of this book based on the notes that I have posted on NTU Pool. Yeah, if you have any questions, please write me. That will help me in writing a better book. Okay? So thank you very much. And I'm leaving on Saturday. You can still see me before then. After that, it's by email. Okay, and let me turn this off. So the last problem set is due today at 11:15. And I hope to grade it on for that. And I think it says that fill out the course evaluation. That is some benefit. Yeah. So thank you very much. Well, I'm very busy right now. Can't have time.
问作业3个评分，这个上次资料改了吗？
作业是就在 Graceful 的。
对对，然后我想要问那个评，就在扣分的问的性质这样子。
哦，
对，
就是那个你是说，如果是 late homework 是不是？如果是你平常晚一天交会被扣？
不是，是那个应该是就是写错了，他就是被改错，就是他觉得我错了就不能被扣了那个。
啊，
对。
那你如果说觉得改的不好，是不是？
就是对。
Okay, regrade. Yeah. Yeah. If you have questions about the grading of any homework, you can submit the regrade request.
OK，
在 Graceful 在 Graceful 上面你可以 submit
OK，
那 regrade. Yeah. 那我就会重改。
OK，
Yeah. Yeah. 可是你要那个这个周末以前啊，你觉得改的不对的，你就submit a regrade request. Yeah.
谢谢。
Yeah. 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 OK， 谢谢你来听。Yeah.
还好，谢谢你告诉我那个线，我一直都写，我写了好多年。
哦，那个宪法的宪。
对。
从南浦吃上来的。
哇，谢谢你，因为
应该会蛮好吃。
对，那这是什么葡萄？
大村的，彰化大村。
我刚刚想说，我来台湾还没有吃过葡萄。
哦。
今天要去买葡萄来吃看看。谢谢。
是哦。
好 ，Yeah。我忘了你是陈建顺，黄建顺，对对，黄建顺。Yeah。OK， 谢谢你来那个上课。希望以后会见面。 你们有机会去美在吗？那可是我都很优秀，所以那个也对我的帮助很大，因为你们是。我鼓励你们，那3本书 ，Differential、Differential Geometry 都过了，想要突击，可是不能快，所以暂时还是要你们要用旧的。